Hello everyone and welcome to lecture 40. So, until the last class we had looked at the optimal input demands. Specifically in the last lecture we looked at the labor input demand in the short run, but prior to that we have seen how to get the optimal L star and K star in the long run as well. And we have also identified what the cost function is. Recall the definition of the cost function. The cost function C as a function of Q is the lowest cost incurred by the firm to produce a certain level of output, right, given the input prices W and R. We are dealing with two inputs, labor and capital, and we are saying the cost function tells us the lowest cost incurred by the firm to produce a certain quantity of output. Now, what we want to do in today's lecture is we want to draw the cost curves, right. So, we want to look at cost curves in general, right. I will do the discussion for the short run and then I will use the short run to derive the long run cost curves. Okay. So, we will primarily focus on the short run cost curves. Now, the reason I want to focus on the short run cost curve is because I know that in the short run we have a fixed input and capital is the fixed input. So, a generic short run cost curve, let me put it on the right and then we will see how to get this. So, I have Q on the x axis, I have rupees on the y axis. Notice the cost C of Q is the fixed cost plus the variable cost, fixed cost plus the variable cost. Now, the fixed cost by definition is a constant number, right. So, that is R times K bar. So, the fixed cost is a constant number and it does not depend on the number of units of output that you are producing. On the other hand, the variable cost, depending on the exact functional form, could be linear or non-linear, right. But the most generic variable cost curve is if you do not hire any labor, you do not produce any output. So, your variable cost is 0 and your generic variable cost curve is going to be something like this. So, this is going to be your variable cost curve. Now, if you add the fixed cost and the variable cost, every point on the variable cost curve is going to be scaled up by the amount of the fixed cost. So, you are going to get a fixed cost curve which is going to look somewhat like this. Now, the gap between the fixed cost and the variable cost is essentially the fixed cost and the this is the total cost, right. The gap between the total cost and the variable cost is the fixed cost. Okay. So, this is essentially the fixed cost plus the variable cost. So, the cost minus the variable cost essentially is going to give you the fixed cost, right. Now, what I would want to show you first is that I can derive these cost curves from my production function itself, right. So, drawing the short run cost curves from the given production function. This is what we want to do, right. So, suppose we are given a production function, I want to use that production function and I want to eventually derive the short run total cost curve. Okay. So, let us do that in steps. Now, there are going to be a few pictures that we are going to be drawing one below the other. So, I suggest we maintain the same order, right. So, first I am going to be having the production function. The production function is going to be in the L versus output space, right. Below the production function, I am going to derive the marginal cost of labor or rather the marginal product of labor first, right. So, let me first get the marginal product of labor which is the output per labor hour. Below that, I am going to draw the marginal cost of labor, right. So, I will leave the x and the y axis blank for the moment, so that we figure out how to draw those curves when we get there. So, for the moment a generic production function could be this particular production function, let us say, right. So, this is the Q versus L. So, this is my production function, right. If you give me the exact functional form, like for example, if you give me Q is equal to L, that is going to be a straight line, a 45-degree line. If you give me Q is equal to square root of L, that is going to be a concave function, right. Now, once this production function is given, I can very easily compute the marginal product by essentially taking the derivative of the output with respect to L Alternatively, pictorially I can think of drawing tangents to various points on the production curve, and I will notice that these tangents are initially first steeper. So, the marginal product is going to be increasing. It is steepest at a point. So, the marginal product has reached its highest point, and beyond that point the marginal product is going to fall. Okay. Now, at the same time, let us also look at this particular cost function and write it as C as a function of Q is equal to the fixed cost, which is R k bar, plus the variable cost, which is the wage rate, times the number of labor units that I hire. But notice, based on the previous examples, we have already seen that the L is going to be a function of Q, right, because depending on the amount of output we want to produce, a short run function is always going to be a function of the amount of output that we are going to produce given that particular k bar. Now, once you give me the production function, I can draw the tangents at various points. So, I know that the tangent here is going to be 0. The tangent is going to be parallel to the x axis. So, the marginal product is going to be 0. Somewhere here I am going to have the tangent which is the steepest. So, my marginal product of labor is going to take this particular shape. This is the marginal product of labor in blue. Now, why are we so particular about the marginal product of labor? Because if I take the derivative of the cost with respect to output, I will be taking the derivative of the right hand side. Well, the first term is actually a constant, R times k bar, that is a constant number. So, that is not going to contribute anything. So, I am going to get the derivative of W times L as a function of Q. The W is a constant number. So, W times dL dQ, right. Now, by definition, I know that the change in cost with respect to output is the marginal cost, right. So, this is the marginal cost, MC as a function of Q is equal to W times, well, dL dQ, I can write it as 1 upon dQ dL. I can essentially invert it, which essentially means that my marginal cost is W upon MPL, right. So, my marginal cost of production is inversely related to the marginal product of labor, right. So, this is the marginal cost of production, right. So, do not get confused with the marginal cost of labor that we talked about. W is the marginal cost of labor. Marginal cost of output is the change in total cost resulting from a unit change in output. So, the marginal cost is of production is inversely proportional to the marginal product of labor, right. So, once you give me the marginal product of labor, I can identify what the marginal cost of production is. Now, the MPL is actually an inverted U. So, the marginal cost of production is going to be the inverse of that. So, I am going to get a U-shaped curve. So, I am going to get a U-shaped curve, but now notice we need to be a little careful, our axes are going to be different. So, marginal cost is plotted in the Q versus rupees per unit of output, right. So, I am plotting the marginal cost of output. Now, that is going to be a U-shaped curve. So, we know that when the marginal product of labor is at its highest, the marginal cost is going to be its lowest. So, the x axis here and the x axis in the third graph are not identical, but what I will say is that when the marginal product of labor is at its peak, the marginal cost is at its lowest, the marginal cost of production is at its lowest. So, think of a particular L producing for which the MPL is the highest. So, the number of units of output produced has been the highest, and there is a certain Q at which the marginal cost is the lowest, right. So, the main takeaway there is that the marginal cost is inversely related to the marginal product of labor. Now, if the marginal cost is the derivative of, so think of it this way, if the marginal cost is the derivative of the cost with respect to output, then essentially if I take the antiderivative, which is if I take the integral or the area under the marginal cost curve, then I should be able to get back my total cost, right. Since the marginal cost is the derivative of the cost with respect to output, the cost is essentially the integral of the marginal cost. I will just change the argument, right. So, taking the integral is nothing but finding the area under the marginal cost curve. So, if I want to compute what is the total cost of producing, let us say, these q units of output, say q1 units of output, I essentially compute the area under this curve, right. So, I integrate from 0 to q, I take a small strip here, right, and then move this strip all along from 0 to q1 and find out what is the total area. That total area is going to be the cost of producing q1 units of output. Similarly, if you tell me that I want to find out the total cost of producing q2 units of output, I will essentially move that strip all the way from 0 to q2. I will find the area under the curve from 0 to q2 and I will tell you what the total cost of producing q2 units of output is. Now, that cost, notice, is going to be increasing. So, alternatively, you could also visualize the problem as the marginal cost is the derivative of the cost curve. These marginal costs are gradually diminishing. They have reached a lowest point. So, that tells me that the derivative of the cost curve corresponding to this q is the lowest, and beyond this point the marginal cost is increasing. So, the derivative of the cost is actually higher, right. So, if I were to draw tangents to the cost curve, they were going to become steeper and steeper. So, let us use this geometric idea and try and get back the cost curve. I also want you to notice that C is the fixed cost plus the variable cost. So, the derivative of C with respect to output is also the derivative of the variable cost with respect to output, is the marginal cost. So, the marginal cost is not just the derivative of the total of the variable cost curve, or it is also the derivative of the total cost curve. Rather, to be more precise, the marginal cost is not just the derivative of the total cost curve, it is also the derivative of the variable cost curve, because recall, the variable cost curve and the fixed cost together gives me the total cost, right. So, in a sense, the blue curve and the black curve are essentially parallel, right. So, they are having a similar trend. Okay. Now, so if I were to now go back and try and figure out what the variable cost curve is, so let me draw another picture here. So, now I have q on the x axis and I have the variable cost and the fixed cost. So, first let us get the variable cost. So, the way I want you to visualize this is by drawing tangents to the variable cost curve, I am going to get the marginal cost values. So, those marginal cost values are becoming smaller and smaller and smaller, which is to say that if I were to draw tangents to a variable cost curve, those tangents should have become flatter and flatter, right. So, now notice, if I had drawn a variable cost curve like this, what would that tell me? That would tell me that the tangents are becoming steeper and steeper. That should tell me that the marginal cost value is going to be increasing. So, that is clearly not consistent with what I see on the graph in this graph of the marginal cost curve, right. So, this can't be the correct variable cost curve. So, to get the correct variable cost curve, what I need to realize is that first, if I were to draw tangents, those tangents are becoming smaller and flatter. So, imagine a curve for which the tangents are becoming flatter and flatter. They have become the flattest at some point here q, right, and then the tangents have become, the marginal cost is increasing. So, the tangents are becoming steeper and steeper. So, if I were to think of a variable cost curve, notice that would be consistent. So, ignore q equal to 0, I can't take derivatives at q equal to 0, so do not worry about it, right. So, if I were to draw tangents to this curve, notice those tangents are becoming flatter and flatter, which is to say that the marginal cost values are decreasing. The tangent is flattest at some point here, it is not parallel to the x axis. So, the marginal cost is not 0, so, but it is still having some slope, but it is flattest at this point, and then beyond this point those tangents are becoming steeper and steeper, right. Now, if I add the fixed cost is a constant number. If I add the fixed cost, then I am going to get the total cost, which is C as a function of Q, right. So, I am going to use TC and C analogously, right. So, the total cost curve is the sum of the variable cost plus the fixed cost. So, this gap is the fixed cost. So, notice what have we shown? We have shown, and in fact, we have geometrically sort of explained why we expect a cost curve, a generic cost curve, to have this particular shape. If we are given the fixed cost and the variable cost, I can start from my production function, derive the marginal product of labor, then invert the marginal product to get the marginal cost, because the marginal cost is inversely related to the marginal product of labor, and then use the notion of area under the curve to figure out the variable cost, then add the fixed cost to get the total cost, right. Okay. So, keep this cost curves in mind. Now, what are we going to do with these cost curves? So, let me first get the, so we want to define, so we know that C is equal to the fixed cost plus the variable cost, right. The fixed cost is independent of output, so I do not need a function of Q. Let us divide both sides by Q. So, I am only looking at Q greater than 0. So, I will have on the left hand side C divided by Q is equal to the fixed cost divided by Q plus the variable cost divided by Q. Now, notice the cost divided by Q is nothing but the average cost or the average total cost. The fixed cost divided by Q is the average fixed cost, average of the fixed cost. But notice the fixed cost does not depend on Q, but when you divide the fixed cost by Q, you are going to get the average of the fixed cost, which is going to be a function of Q, right. So, if your numerator is a constant number, but you are dividing it by a Q which is becoming larger and larger. So, essentially this entire ratio is becoming smaller and smaller. So, AFC is a function of Q, and then variable cost divided by Q in general is going to be an average variable cost curve as a function of Q, right. So, my average cost is total cost divided by Q, average fixed cost is the fixed cost divided by Q, and the average variable cost is the variable cost divided by Q. So, think of any aggregate divided by the number of units to get the averages. All of these are going to be measured in rupees per unit of output, right. Now, the thing that we are interested in is how do these curves look like, right. So, let us start with, so since I already have the variable cost and cost, let me actually draw them once more here so that you can see them properly. So, I will first get the fixed cost, then you have the variable cost, and then you have the total cost. And on the graph below, let us get the averages of these, the unit of output. Now, the average fixed cost is the fixed divided by Q, right. So, what does that tell you? As my Q increases, as Q goes to infinity, your average fixed cost is going to tend to 0, because you are dividing by larger and larger values, right. So, notice your average fixed cost is the cost divided by fixed cost divided by Q, right. So, the average fixed cost as your Q goes to infinity is going to go to 0. So, what this means is that if I start with, when Q is very small and tends to 0, my average fixed cost is going to be a very large number, and as Q goes to infinity, my average fixed cost is going to tend to 0. So, this is average fixed cost as a function of Q. Variable cost divided by output. Recall, AFAVC is going to be the variable cost divided by output. So, this essentially means if you have just the variable cost and I want to geometrically think of average variable cost, just connect the origin. So, let us say for this Q I want to find out what is the average variable cost. So, draw a line from the origin to this point, find the angle, get tan of that angle. So, that is the variable cost divided by the Q. Then for some other Q, notice, just connect the origin to that particular point, get tan of the value. So, now notice the angles are becoming smaller, but now notice beyond a certain point, let us say I want to find out what is the variable cost for some particular Q here, then again I will connect the origin to that particular point, that angle now is going to be much larger, right. So, initially I am going to get the tan values which are going to be smaller, and then those tan values are going to be increasing. So, if I look at the average variable cost, let me draw that in blue. So, this is where the AFC and AVC are going to be equal, and initially notice that the ray connecting the origin to the fixed cost curve is going to be steeper than the ray connecting the origin to the variable cost curve up to this point, which is to say that my AVC is going to start here and then is going to take a U-shaped curve, right. Now, why does the AVC take a U-shaped curve? Because initially Q increases at a faster rate compared to variable cost, right. Why? Because your marginal product of labor is increasing as you are hiring more and more variable inputs, which is the, let us say, labor. As you are hiring more and more labor inputs, your marginal product keeps increasing. So, the output is increasing at a much faster rate compared to the variable cost. So, the denominator is increasing at a much faster rate compared to the numerator. So, the entire ratio is actually decreasing, which is to say that my AVC is actually decreasing. But beyond a point, diminishing returns will set in. The marginal product of labor will only increase by a tiny amount, which is to say that your Q is only going to increase by a tiny amount, but your variable cost is going to increase by much more, right. So, because you are adding more and more labor hours, but because of diminishing marginal product of labor, the output is not increasing at a very fast rate, which tells you that your output is increasing a very, very tiny amount compared to the variable cost. So, the numerator is actually increasing at a much faster rate compared to the denominator, which is to say that the entire ratio is actually increasing. So, the AVC is actually increasing. Additionally, I know that as Q goes to infinity, average fixed cost goes to 0. So, your average cost is actually going to converge with your average variable cost curve, right. So, as Q goes to infinity, the average cost is going to converge to the average variable cost curve, because your AFC is going to be 0. And if I draw the average cost curve, it is going to look somewhat like this. So, as my Q goes to infinity, my average cost is going to converge to the average variable cost. Okay. So, I hope these graphs are clear. What I would suggest at this point is to pause for a few moments, try and draw the fixed cost, variable cost and the cost curves yourself, and use these graphs to get the corresponding averages, the corresponding average fixed cost, the average variable cost and the average total cost or the average cost. I will give you specific examples which will also help you understand and draw them better, but it may be a good idea to actually pause for a few moments and try and draw them yourself. Okay. So, now we have the average fixed. So, what do we have? We have the following terms. The fixed cost we have seen. We have also seen the average, in fact, the fixed, we have seen the variable cost, we have seen the cost, we have also seen the corresponding averages, average fixed, average variable, average cost. Now, if you think of the only part or the only missing link, that is the marginal cost, right. While we have an understanding of the marginal cost curve, what is missing here is that how does the marginal cost curve compare to the average variable cost and the average cost curve, right. The units of all of these is rupees per unit of output. The units of all of the ones here is in rupees. So, always keep this in mind. Okay. So, the question that we are asking is, how is the marginal cost curve related to the AVC and the variable cost curve, right. Notice that I already know what my AVC and AC look like per unit of output. I know that my AVC is a U-shaped curve and my average cost converges to the AVC as Q goes to infinity. Now, what does the marginal cost curve look like? So, to do that, let us first start with the, so I am going to look at how the marginal cost is related to the AVC curve and how the marginal cost is related to the average cost curve. I will leave that as an exercise for you, right. So, start with the AVC curve. We already know that my average variable cost is essentially the variable cost divided by output. Suppose I take the derivative of the average variable cost with respect to output, right. Essentially, I will be taking the derivative of the right hand side, which is the variable cost divided by output. So, if I take the derivative on the right hand side, now notice I have a function which depends on q both in the numerator and in the denominator as well I have q. So, essentially I can use the division rule of derivatives or the u upon v rule, which essentially says, so if I take the derivative of the average variable cost, I will have the q, right. So, the denominator times the derivative of the variable cost. So, to not clutter it, I will avoid writing Vc as a function of q. So, q times the derivative of variable cost with respect to q minus the variable cost times the derivative of q with respect to q divided by q square. So, this is the right hand side that I have, the derivative of Vc divided by q, or the derivative of the average variable cost. Now, on the left hand side, I have as before the derivative of the average variable cost. Now, what do I have on the right hand side? It is q times the derivative of variable cost with respect to output. Now, what is that? We already know that the cost is essentially the fixed cost plus the variable cost. So, the derivative of the cost with respect to q is the derivative of the right hand side, which is the variable cost with respect to q, and by definition that is the marginal cost, right. We already know this. So, the derivative of the variable cost with respect to q is the marginal cost minus the variable cost times the derivative of q with respect to q is going to give me 1 divided by q square. I will do a little bit of algebra. So, I will take the q outside. I will write this as the marginal cost minus the variable cost divided by q square. I can cancel, since my q is greater than 0, I can cancel one of the q's here. So, I have d upon dq of AVC is essentially the marginal cost minus Vc divided by q is the average variable cost, and then I can get rid of one of the q's here and write it as q. So, what does this algebra tell me? It tells me that if I want to understand the derivative of the, how the derivative is going to change of the average variable cost with respect to q, I essentially have to look at the right hand side, which is the marginal cost minus the AVC divided by q. Now, notice what does that tell me? It tells me that in this zone, on this portion of the AVC curve, the average variable cost is actually decreasing. So, its derivative is going to be negative. On this portion, the average variable cost is actually increasing, is upward sloping. So, the derivative of the average variable cost with respect to q is going to be positive. And then at some point here, the average variable cost at the lowest portion of the u, the derivative of the average variable cost with respect to q is going to be 0, which tells me that the tangent to the AVC curve is going to be parallel to the q axis or the x axis. Okay. So, let us make use of this. So, what do I know? So, let us start with the left hand portion, which is that the AVC. So, if the derivative of the AVC with respect to q is less than 0, which is to say that the AVC is decreasing, that essentially means that this right hand side, marginal cost minus the AVC upon q, is less than 0, because the derivative is nothing but the marginal cost minus the AVC divided by q. Q is always positive. This essentially means that the marginal cost should be less than the average variable cost. So, the takeaway here is that when the average variable cost is decreasing, the derivative is less than 0, which means that your marginal should be less than the average, which is sort of expected, right. So, think of your average monthly income, right, and so let us say the average monthly income of 5 individuals is their total income divided by 5. So, let us say that is rupees 1 lakh. Then you added a 6th person to the group. If the 6th person's monthly income is less than 1 lakh, which is let us say 80,000, then by adding this 6th person, the new average is going to be lower than 1 lakh, right. So, the total income of 6 people divided by 6 is going to give you a number which is less than 1 lakh. So, what this means is that if the marginal cost is lower than the average, if the marginal is lower than the average must fall. Similarly, we can write down what happens when the derivative is positive. Let me quickly write this. So, when the derivative of the average variable cost with respect to q is greater than 0, that means that the average variable cost is increasing, which essentially means that MC minus AVC divided by q is greater than 0, which is to say that the marginal cost is greater than the average variable cost. So, that tells me that when the marginal is greater than the average is increasing. So, finally, since these are continuous functions, what does it mean to say that the average variable cost, the derivative of the average variable cost with respect to q is 0? So, AVC is at minimum, right, because essentially the tangent to the AVC curve is parallel to the x axis and the average variable cost curve is a U-shaped curve. So, the tangent is parallel to the x axis. So, that tells me that MC minus AVC by q is exactly equal to 0, which means that the marginal cost is exactly equal to the AVC, right. So, let us make use of this and connect all of these dots. So, when the marginal is less than the average is falling. When the marginal is greater than the average is increasing, and the marginal is equal to the average at its lowest point. So, if I make use of all this, I can draw the marginal cost curve. So, when the marginal is lower than the average variable is decreasing. When the marginal is greater than the average variable is increasing, and the marginal is exactly equal to the AVC when the AVC is at its minimum. Now, this I did for the average variable cost curve. Now, instead of average variable cost, I could also start with the average cost and write it as, if I want to look at, so I will leave that as an exercise for you to try. So, average cost is essentially the cost divided by output, right, and I would want you to take the derivative of the average cost with respect to output. You are going to get some expression. That expression is going to turn out to be marginal cost minus the average cost divided by q, right. So, check this, and then you can accordingly write three similar statements that I wrote previously here. When is the average cost curve increasing, when is the average cost curve decreasing, and when is the average cost curve at its minimum? You will find that they are going to be similar to the analysis that we just did, and you can say that the marginal cost curve not only passes through the lowest point of the AVC curve, it also passes through the lowest point of the average cost curve. So, in the short run, the marginal cost curve passes through the minimum points of these curves. So, we will take an example and we will try and draw the average cost, average variable cost and the marginal cost curve, and our next interest is going to be to move from the short run to the long run. We will do this in our next lecture. Thank you.